Hello there! In today's video, we will look at an exercise of individual risk model under the question of what is better, to gamble or not to gamble. We are team number 3, made up of Edson Martinez, Lily Perez, Pau Zamora, Erika Villalpando, and myself, Rosangel Medrano. First of all, we will review some important concepts to start working on this exercise. The risk concept has many meanings depending on the area. From a mathematical approach, insurance and gambling are some of the phenomena that we will be talking about. From a philosophical point of view, we're both referred to different things. Risk can have a positive or negative effect. However, they usually have connotation of loss. The risk we will be talking about as a chance that an outcome or investment actual gains will differ from an expected outcome or return. The one fundamental difference between gambling and insurance is that gambling increases risk while insurance decreases. Those who bet are risk lovers, while those who insure are risk adverse. The tools that we will be using are common to this theory and also to the actuarial science in general. Let's gonna see about the geometric distribution with my team member, Pau Zamora.
Thank you, Rosangel. Now I am going to talk about the geometric distribution. First, we have to consider that this was the procedure that we developed to discover the impact of the rules of this game on the player. We know that the total number of possible outcomes when rolling the 2 dice is 36, but only 6 cases are considered a success. So the probability of success for the player is then 1/6. On the other hand, we have that the probability of failure would be of 5/6. Now that we know these probabilities, we can determine the probability that the player has to pay only $1. This is that if he only fails once, which would be as a result of multiplying 5/6 for 1/6, this would be 5/36. Then we know that the total number of possible outcomes when rolling the 2 dice is 36, but only 6 cases are considered a success. So the probability of success for the player is in 1/6. On the other hand, we have the probability of failure would be 5/6. With this, we can determine that the random variable of loss behaves as a geometric random variable, and we can determine its probability mass function. This is that the n, that is the random variable, equals n, that are the possible amounts of lost weights, and this is represented as the expression listed below. Now I am going to talk about the inverse transform technique. This is a basic method for generating sample numbers at random from any probability distribution given its cumulative distribution function. This will be a tool for the simulation of losses. But we have to understand that this is based on the weak law of large numbers. This says that the distribution that follows this random variable is a series of simulations of loss to obtain an average and thus determine a fair value that the player must charge to enter the game. This will be an excellent tool for making a Monte Carlo simulation, and we will watch this later. Now my partner Lily will talk about the wealth ruin process.
Thank you, Pau. Now we're going to talk about the wealth, or also known as the ruin process. First of all, what means wealth? According to the dictionary, wealth is anything that has utility and is capable of being appropriated or exchanged. The ruin theory is a stochastic process that increases continuously because of earned premiums and decreases stepwise at times that claims occur. When the capital becomes negative, we say that ruin occurs. This process is a useful management tool which indicates instability. Now let's watch an Excel to see the practice.
Okay, so in the first column here, we have the support of the random variable, which means the number of dollars we could lose. In the second, we write the mass function, and in the third, the probability distribution of the geometric random variable. Now, by this parameterization of the distribution, we can have the amount of money that we will lose until the first double outcome appears. So as you can see here, this is the parameter we're using, 1/6, because it's the probability that the outcome will be successful to us. Okay, so from the second row on, we copy this expression, and then in column C, we just start accumulating these results. So for instance, this result here is the sum of this one, and this one here is the sum of this and the previous one, and so on until we get at 1. Now here we insert a dispersion graph to take a look at how this mass function behaves. That is the mass function of a geometric random variable with parameter, as I was saying, 1/6. Now in here we have the first 3 columns I just showed to you. They are the same, just that in this column here, the accumulated probability of the distribution function, we start at 0 instead of putting this. That's the only difference. And here in column D, we just have once again the support of the random variable. Okay, so now we will use the inverse transform technique to simulate the losses in the experiment. In the column control, we just write consecutive numbers. In the next one, we generate a random number between 0 and 1, which is a probability. And in the last column, we see realizations of a geometric random variable by means of the inverse transform technique. So in this column, we just use this function, buscar b, to look for the number that we just generated in column H, a random number between 0 and 1. We look for this in this range on column C, and once it finds an approximate result, it returns the number that it's on the right on column D. So we repeat this experiment many times. In our case, we did 25,000 simulations. So if this number is between 0 and the probability that the accumulated distribution function gives us 0, then the loss will be 0. If the number is between the distribution function in 0 and the distribution function in 1, then the loss will be 1, and so on until the nth outcome. Okay, so in column E, we count first the number of times that we got a 0 in our realization column. And then we divide it by the total number of realizations. We repeat this, and we just copy this formula to find the same thing for 1, 2, 3, and so on. Now, as you can see, this number here resembles this one. And in general, all column E resembles column B. Now, this happens because we are using the weak law of large numbers and the Monte Carlo simulation technique. Now, here you can see the comparison between the graph I first showed you and the one with the simulations we just did. As you can see, they are very much alike, and the resemblance will be even bigger if we did even more simulations. Okay, so now we are going to calculate an approximation of the expectation of these random variables. Now, this can be done in many ways. First, here we compute the sum product of these 2 columns, and we get a result that is really close to 5. Then, here we are using the parametric expression for the expectation of the geometric random variable with parameter 1/6. and we get a 5. We can also compute the average of the simulated values we just got, like this, or obtain the same results by computing the product between these results here and these other results. Okay, finally, another way of doing it is just by adding the survival function until the support of the random variable. Here we have the survival function, which equals 1 minus what we have in column C, the accumulated distribution function. And by adding those results, we get again a number that is almost 5. So what if we could charge for each series of trials? How much will we charge? We have a Markov chain process called the wealth process, which starts at a certain initial point, in this case 2, which will be our initial wealth. And then we add a certain level of premium. In this case, we take 5 because it is the expectation of the random variable we just calculated. And then we subtract from that sum the amount we will be required to pay, which is a random loss. And we repeat this until time 10. So in this graph, we show the results of these simulations, a random walk through the wealth process. As you can see, there are times where we're losing money. We can continue to simulate and obtain different trajectories of the wealth process. And notice that the probability of ruin, of going below the level of zero money, is very large, at least with these levels of initial wealth and premium.
Now we are going to calculate the probability of ruin. At the beginning, we have an initial wealth of $2 and a premium of 5. We put this up to 10 series. On the time 0, we just put the initial wealth. On the time 1, we put the initial wealth plus the premium. Next, we use a function VLOOKUP where we generate the random number that we are going to look for the distribution function range for the geometric random variable. Then it will return the number on the second column. We have a representation of the wealth process. To see if the process is falling to ruin, we ask in this column if there was a time we went below the 0 in money. If this was the case, we write a 0. Otherwise, we put a 1. Then we repeat the simulation 25,000 times. Next, we compute the probability of ruin by calculating the average of the numbers on the column L. We can see that with these numbers, there is a large probability of ruin. If we increase the wealth to 5 and the premium to 8, we have a smaller probability of ruin, but it still is very large. With an initial wealth of 7 and a charging premium of 12, we can decrease the probability of ruin only to 4%. Finally, we can say that we are able to prevent catastrophes by using random variables, the inverse transform technique and the Monte Carlo simulation technique under the context of risk theory.
Thanks for watching. Do not forget to click in the like button if you enjoyed. Subscribe to this channel and click the bell so you can get notifications when we upload a new video. Bye!